Ciao, salve, benvenuti or welcome to this episode number 4 of the series Tuesday Night Live with me and Emanuele Bonin. Ciao Emanuele.
Hi all. Happy Tuesday night live to you all.
Allora, I'm mixing Italian with English now. So I was saying, welcome to this episode number 4. So we've been with the one of today. It's been 1 month basically that we've been streaming, me and Emanuele together. As you can see, his English is improving.
Yes, the cat is under the table again.
Yeah. So as you know, this series is about us covering topics. The topics will be random. Right now we are covering how to program the VIC2 chip. We are trying to show you how to have a stable raster line on the screen. And we have other sessions ready, let's say that, in relation to this. But each Tuesday we will cover such small topics because these things will not be big in terms that they will take a lot of, we take a small thing and we explore it and try to show it to you so that you learn to do the same thing. Ciao, Fraction. Hello.
Hi, Fraction.
So, yeah, this series is about things that will help you, let's say, code better on Commodore 64, Amiga, or whatever. But normally it's a Commodore 64 and it's related to the challenge, okay? Also to the game jam. Okay, so let me start with the usual stuff. So please subscribe and like my YouTube videos. Today or yesterday I released our stream number 3 that we did last week, and I'm just going to say something because most people do not realize. Please look under the comments of the video, okay? There are the links where you can get the source code, as I am indicating here. You can get the source code for each episode. Same thing, please go to the Retro Programmers Inside YouTube channel, subscribe, like. This is the best thing you can do because we want others to learn, and to learn we need the videos to be spread, and YouTube only spreads videos that are liked. Let's put it this way. So the more you like them, the more they get spread. And don't think I'm not subscribed is because I'm not logged in. So don't think I'm not subscribed to the Retro Programmers Inside.
Hi, Massimo Bonucchi.
Ah, ciao Massimo. Bonucchi.
Okay, your pronounce is very well.
Perché in Maltese it is said Bonucci. Okay? Because that surname exists in Maltese.
Okay.
Anyway.
I don't know.
That's why I pronounce it without the H sometimes. So apologies, Massimo. But yeah. So also please note that there is my Facebook page where there are all the stuff that I release, and same thing. So please like, follow, etc. as always, and same thing for the Retro Programmers Inside page. Please May I remind you that there is the PONG Game Jam. The date has been extended. It is till the 30th of June. That means it will finish not next Tuesday, but next Thursday, okay? So on the 30th of June, and probably the live where I will show all the games, it will happen either the 5th, which I doubt it's too close, or the 12th, okay?
Yes.
That's when the live might happen. So please, there are lots of people that participated in the Pong challenge, and there's some excellent work. The same thing, I have the Phaze101 Facebook group. Please subscribe, like there, and same thing, Commodore Dev. As you don't know, some people call me Commodore freak because I'm only it's not I'm only interested in Commodore, that's not right. But I only have time for Commodore. That's true. I like all the other machines, but I cannot really dedicate time to the other machines. So Commodore machines 8 and 16-bit is fine. And so I have this group where I also thank Colin, Vella, and Colin Vella, as you see, he's an excellent programmer for the Amiga. He's doing this game. You know him, he's done Barbarian and lots of other games. And there is also Walter Mama, who is, I thank them both. He is very good in hardware. So if you like what I do or what we do, and you want to get in touch with us, please subscribe to our Discord channel. Links in the upper right hand corner of the screen. But I think if you type Discord, it will give you the link to Discord. I do read messages on Facebook, but I take time. I'm more faster on Discord. Also because of the way it's easier to manage the messages on Discord than on Facebook. If you like what I do, please, and want to support me, you can unlock 60 videos if you subscribe to Patreon, or the same thing on Coffee. If you just want to do a donation, then you can do the donation. I have a page for donations, which I think you can also get. The command is !donate, I think it is. Yeah. So besides that, I know I repeat this, but there's this page for those that follow me. Friday, Saturday, Sunday, things related to the Amiga. This page is your Bible to learn 68,000 to program the Amiga. There are all links related to development. I do update this link, this page, once a month or so, roughly. So yeah, keep an eye on it and look what I add. The other thing is I released the source code, and also I released the exe, and I made it as a downloadable exe that you can run it from hard drive, or you can run it from a floppy drive of the Let's Make an Amiga Game series. You can access the videos on YouTube. I'm releasing one every week now, and the source code is already available for those that want to follow. Most important thing is that you read these, you click on these links and read the comments that I have there. While I'm here, please note, I like to thank Megastal for the backgrounds, sprites, Megastal, Hound Dog, and myself, music, Crane, and Mr. character Naufrago. And also thanks to go to Massimo Bonucci for the original idea. So, yeah. Anyway, so let's move to Visual Code. Before we start, today I do not want to make the mistake that I made in the others. I'm going to show you what we are trying to do. Okay, what we are going to teach you today. So let's run this. So you can still see that we still do not have a stable raster, okay, on the screen. But what we tell you today in this episode, what we tell you today, we have two sources. I don't know if we will manage to do them both, but the first one is the one that you're seeing. It will, if we manage to do the second one, you will see a stable raster. Okay, and I think the lesson of today, let's call it lesson. I don't think it's right to call them lessons, but let's say what we are covering today, it's quite interesting. It's quite how to say, it's really good to know, so that when you look at certain demos, etc., you can start understanding what they are doing. So although you're not seeing it stable, I can assure you the next one, okay, I have two sources here, you can see them, okay, the number 4, okay, this is 302, number 4 is the raster will be stable and it will be perfect. So let's close this and let's pass this to Emanuele. So Emanuele, okay, is going
James,
to
James,
is going to explain things, but he will have to stop. Okay, he will have to
Okay.
stop after a while, and I repeat what he said. It's good to
Okay.
repeat, and so that you learn it better, and also to give him to make him rest a bit, because he is, remember, his English is not like mine that I can speak it, even though I don't consider myself my English is good, but I can speak it while I'm doing coding, while he has to think about the code and also about the English. So bear with him, okay? I can see improvement from the first episode that we did till the fourth one. So bit by bit, this will improve, okay? So Emanuele, you're there? You can
James,
start.
James, we have a problem.
Which is?
My Visual Studio Code has ended the session, and I can't rejoin to your
So
session.
you need, okay.
It's just happened.
Yeah, it's okay. So I need to send you the link, no? So I'm sending
Yes,
it on Discord.
yes, it's okay.
So while Emanuele is preparing for this, I just want to remind you about the Game Jam. Remember, you have till the 30th. Please send it to the email that is written on the Retro Programmers Inside Facebook page, so that we can show it on the 12th, probably 12th of July.
Okay.
Give me a second, Emanuele, because now we need to make sure that you have both sessions.
Yes, I can see both session.
You can see both.
Yes.
Okay, so I'm going to follow you now. Okay, so you can start.
Okay. First of all, I must say something about a thing. I realized that in preceding episodes, I was too much worried how to say things in English, and I forgot about manners. First of all, I wanted to thank Prince Phaze101 for giving me this opportunity to expose what I wrote in Italian, also in English. Also, I want to thank my collaboration of RPI group. Without their invaluable help, many things would not have been possible. In sparse order, Francesco Clementoni, Giuseppe Pintus, Davide Fichera, Giuseppe Mignonia, Orazio Cacciola, Lorenzo, Massimo Bonucchi, Nello Galliano, and last but not least, James Phaze101. And finally, I want to thank all those who have followed and are following this live in the hope that it will be useful to those who want to approach retro programming in general and Commodore 64 in particular. After thanks due, we can continue with the technical part of the live.
Cool. Yeah.
I brought I brought and read.
It's okay, but I have to say, it's true. The people in behind retro programmers inside, okay, they are all coders. They are very good coders,
Yes.
and most of the things that we do, including myself, would not be possible, okay, without them. Okay, so yeah, it's right to actually say this. I'm when I start, I always think about the page and to make advert to the page, etc. But yes, it needs to be said that without these people, we will not be where we are. So yeah, thank you also from my side.
It's true. It's true. Okay, start again. uh, um, in this piece of code of this night, I can remake the code of the last episode with some difference. The main difference that I explain fra poco, come si dice?
Uh,
Non mi ricordo.
in a minute, that he will
In a
explain in a
minute.
minute. Yeah.
That I will explain in a minute, is about the presence or not of kernel and basic. Okay, this program, like the other, show a little raster line on the upper border of the Commodore 64. Okay, this is now I comment in velocity the lines. If there are some questions, please stop me. Okay, this is the start of the code.
Yeah. Can I stop you a second, Emanuele?
Yes,
Uh,
yes,
so actually, this is a good point what he said. This code continues on the one that we did last Tuesday. Most of the code is similar. Emanuele is going to repeat it, okay? He's going to go through it, maybe faster, because it's no use repeating everything from the beginning. But what you need to understand is that there is a slight difference, very small difference from this one to the previous one if you had to compare it, okay? And that is that now we are switching the kernel and basic off, okay?
Yes.
That's the main point behind this one. Okay, Emanuele, please proceed.
Okay. So this is the entry point of our code. These are some constant.
Constance? Mm-hmm.
The raster line where we want to show the raster beam passage. The register for counting the raster beam position, the other register to see the raster beam position, the register for the interrupts that can say this register say us what type of interrupt is triggered. Okay, so this is the first part of the code. First thing that we must say with this in this program is disabling the maskable interrupt that are interrupts that can be stopped by the system with this opcode. So we continue disabling the CIA interrupts and clear them with these codes that load some value, the right values mask on epsilon in this case, and place it in some register that la cui funzione è quella di pulire gli interrupt.
Okay, so first of all, when Emanuele says epsilon, it means Y, okay? Y register. And when he says X, it means X register, okay? That's the first thing to clear out when it comes to registers. So basically, here, okay, I'm just going to do till here, okay, Emanuele, so you can continue from down here. So this is for those that use Kickstart assembler, okay, these codes are all using Kickstart assembler. We have the entry to our program, okay. I need to switch you from following you.
Okay.
Okay, so this is the entry to our program. Basically, this entry here means start the program from this label. Okay, here are our constants, which we covered last week. This is switch off interrupts. Okay, it's a 6502 instruction that disable the interrupts. Okay, then we are loading 7F and storing it, okay, in these two locations registers, okay, in these two register locations, because if you recall from last week, and I'm going to bring it back, there is the memory map and DD. I'm quite DD
0D.
You can see it here is the CIA, okay, interrupt control register, okay. This is, yeah, the DOD. I'm doing the DOD. It's the same thing. They are a copy of each other anyway. So basically, he's disabling the interrupts with this value, okay, and he's also making sure that if there were any interrupts happening, he's clearing them, okay. That is basically it. That link of, let me share it again. This page, okay, should be your reference when you're coding the Commodore. I always have it open when I'm coding the Commodore 64. Okay, it's the memory map of the Commodore 64 and its address registers, okay? But what each address does. So keep it, treasure it. It's an important link. You cannot, as you'll be constantly looking at a book, and you'll be very slow. So
is the Bible.
yeah, it's like the Bible, yeah. So far we have just cleared the interrupts and make sure that we disable them. Now the new part, Emanuele is going to talk about this part. This is the new part, okay? So please listen careful to what he's going to say. Emanuele, you can, by the way,
Okay.
I can probably just give me a second before you start. Maybe I
Yes.
can put this here. I don't know if you can read it, but like this, it should help, because he's going to talk about register or address register O1, okay? And he's going to show what he's going to do. Okay, Emanuele?
Okay. At the end, this piece of code is the same for all my interrupt programs. So when we have when we know what is it, we can use it by copying it and placing it where is useful. Okay. Now the new part. This is the difference comparing with the other program of the last episode. The difference is that in this case we take kernel and the basic ROM and switching off it and the switching off.
Yeah, we switch
So
them off, yes.
so we can't use kernel routine or basic routine from here to the end or until we switch on it.
Mm-hmm.
Okay. In this case, we until the end.
Mm-hmm.
Okay. First of all, we must choose the value for our configuration, that is this in this case.
Okay, can I stop you there? So
Okay.
why he has chosen that value? Okay, so we are only interested, to be fair, in the first three bits. Okay,
Yes.
the other bits, okay, 4 and 5, you can see here 4 and 5 are for the data set, and when you put a 1, it means no button is pressed on the data set and the motor is off. Okay, that's what it means. Okay, so that's why I had to put 1 and 1. Now the first one, 0 and 1, you can see here 0 and 1 means Okay, RAM visible at A000. That means where the basic ROM is. We see RAM instead of the ROM, and where the kernel is. Okay, so that's how you switch them off, by having these two bits set to 0 and 1. The other one, okay, this one, the bit 2, we need it on because it's the IO. Basically, it's the registers of the VIC. We need to use them. Remember, the registers of the VIC are between D000 to DFFF. Okay? Hence why we need that one there. Okay? Continue, Emanuele. So,
Okay, I'm waiting
yeah.
for your sign. Okay, when I choose the right value for our configuration, we place it on the first the second byte of um, on memory map of Commodore
Mhm. It's address 01. Yes.
01 that have the most important configuration for the Commodore
Yeah.
64.
So address 01,
But is not okay.
address 01 is how the Commodore, you always, it's the configuration register or processor port as it's called here, where you tell it, okay, what configuration of memory you want. And it's quite an important address 01. Okay, continue.
Okay. The vector, the two contiguous bytes of the interrupt handling is read starting, in this case, from location FFFE and FFFF. These two bytes contain the interrupt handling address. We can use these two bytes because we have switched off kernel and basic.
Okay, Emanuele, I suggest that you read your own notes so that you don't struggle.
Okay.
But I'm going to add something to it, okay? Because for those that do not know the memory of the Commodore 64, so I'm going to go to the end. This address has got the address of the interrupt, okay? And normally that is hard coded, let's put it this way, because the kernel is on. But if you switch off the kernel, okay, and you get RAM instead, then you have access to this memory location and you can change it, okay?
Yes.
And what Emanuele was trying to say is that when we had the basic and kernel on, we could not do anything to it as in the previous examples, okay, because basic and kernel were always on. Now that we switched it off, we can create what is called a real interrupt routine, okay? And he will explain that. Continue, Emanuele.
Okay. The routine will be real because, unlike the routine presented in the last episode, this routine have to save the CPU registers A, X, and Y, and the status register before any operation, and to be able to restore all the values at the end.
So that is what makes the difference between
Yes,
the interrupt routine that we were using before. Remember, we were using address 314 and 315. And now, and we were not saving anything, we're just pointing it to it. But now we need to have a status of the you need to save the registers before as soon as you enter your interrupt routine. This is the same for those that were following me on the Amiga in the last few weeks. Okay, we save the registers when you create your interrupt on the Amiga, the same thing. So the principle is always the same, okay? Whether you're doing 68,000 or 6502, you always save the registers. I'm talking hardware programming and leaving the OS behind. In the case of the Commodore 64, basic and kernel is the OS, okay? In the case of the Amiga, is Workbench. When you eliminate both of these, okay, you are using the hardware directly, and because you're using the hardware directly, then you need to do certain things.
And
Hello, Proton.
Hi, Proton. Can I continue?
Yeah. Continue.
Okay. The register must be saved because we want to avoid the issue after execution of our routine. After the restore of the CPU register values, we must use RTI opcode, return to interrupt is the acronym, instead of jump. Unlike the last time we have used the jump to return to the OS, the basic basically. Sorry for the joke of word.
So basically, last time we were using the jump because we were returning back to basic. So yes. Jumping back to where we left from basic. While now we don't have basic, so we need to return from it using RTI.
Okay.
Yeah. I think
now we like the other routine in the other episode. We must load the low part and the high part of our routine that I called my IRQ.
Yeah.
We modify the interrupt vector, that in this case is FFFA and FFFF instead of 0314 and 0315 when we had basic and kernel switched on. Okay, these are the biggest difference. The other thing are similar. We load our the value of the raster line that we want to display, and we store it on the raster register DO12X. The raster line position is lower when 2056, so we must set the bit number 7 of DO11, control register 1. This bit is used to manage raster line over 255. So we are here we resetting the bit number 7 of register DO11. Okay. And now we set in the register of the VIC, which is responsible for the interrupt events. So as to a trigger an interrupt when the raster line will reach the number indicated by the registers DO11 and DO12. The bit 7 on DO11 plus the 8th bit on DO12. So we use this activation mask that activate the raster beam interrupt setting the bit 0 of the register DO1A, where we saving the new configuration. And now we enable again the normal interrupts routines. Okay, so from here until the end or the other chains, the interrupt will call our myERQ routine that is placed here. But when we re-enable interrupt, we must ok, noi dobbiamo scrivere qualcosa per impedire che si blocchi tutto.
Okay, what he's saying is when we enable the interrupt, okay, we need to write something, okay, so that it doesn't block, basically. Yeah.
Okay, so in fact, it is not a good idea to come back to the operating system because it simply does not exist anymore. So we can't use RTS, but we can simulate the operating system loop. The operating system basically is a loop that waiting for something like keyboard pressing, joystick moving, or commands to read and write in the disk or in the tape. This is in a nutshell. With the operating system loop, with an infinite loop in this case, that we use to incrementing the upper left byte on the screen to display the changing after each frame. Okay. So we make a jump infinite loop.
Yeah. So I'll stop you there. So what Emanuele has done, I'm going to take control, Emanuele. Okay, so we disabled basic and kernel. Okay, we point the register or the addresses or the address, the 2 bytes at FFFE and FFFF to our interrupt routine, which is down here, which we haven't yet done. Okay, we set the raster line where the interrupt needs to happen, basically, and we make sure that the high bit 8 of the O11 of the raster line is 0. Okay, then we set we enabled, basically we told it we need to start interrupting, basically we want our interrupt, and for that, when the screen vanishes is because I'm looking for this. Okay, so we have a 1 there. Okay, so bit 1 is raster interrupt enable. Okay, so we're telling the I was going to say the Amiga, the Commodore 64, we want a raster interrupt. Okay, as you can see, this register is used for other interrupts too. You can have a sprite to background collision interrupt, you can have a sprite to sprite collision interrupt, or light pen, which we don't use and won't cover. But in our case, this is the interrupt that we have enabled and that we want to happen. Okay, so every time this interrupt happens, our routine, which is called my interrupt, will execute. Okay, and it will simulate like something is still going into the computer by incrementing in the upper left hand corner the bytes on the screen one after the other, so to show that something is happening. So we have an infinite loop here basically, while we can see our interrupt routine happening. Okay, we cannot return to basic, as we said, because there is no basic and there is no kernel too.
Yes.
Okay, Proton, what you are trying to say?
Yes, Proton, please.
So now Emanuele will explain the my IRQ, okay?
Okay.
Which is the routine that will be
If
executed.
Proton won't say something,
I mean, in the
you
meantime,
can write.
yeah, which will be executed every time the interrupt happens. Okay.
The interrupt happens when the raster beam reach
Yes.
the
The number we
line
specified.
number 30.
Yeah, I
in
mean,
this case.
I don't remember. Yeah, we said 30. So every time we reach raster line 30, an interrupt happens and we get this to execute, basically, my IRQ.
Yes.
Okay, I'm going to give you control.
Okay. So here is the first thing that we must we have to make. We must save the status register and the register AXY, like said a minute ago. A minute ago, yes. One way, there are two ways to save the register. One way to save and restore the status register is the using of stack with the instruction PHP, push processor status register, and PLP to retrieve it, pull processor status register. These
Okay,
are
Emanuele, can I stop you a second because
yes.
Proton wrote. So Proton is saying when the kernel is off and you are using the CPU vectors, you should also hook up the non-maskable vector
interrupt.
also, FFFA and FFFB. If it remains unset, any MEI may crash the system. True, but in this case, we do not want to complicate things, and that's why we said we're simulating the OS in a way. But yes,
Okay.
yeah, and I believe.
Thank you, Proto. I don't know this. Sorry, James.
No. What were you saying, Emmanuel? I didn't get you.
Thank you, Proto. I don't know these things.
You didn't know this. Yeah. Okay, but in our example, we are not going to have a no maskable interrupt MEI because we are locking it basically. But yes.
Why Proton the PHP and PLP isn't to use in the ERQ? Saves the status already. Is unnecessary, useless. Okay. Okay, thank you, Proton. I don't know this too. Okay, thank you. So this part is It's
Well,
not useful.
you continue with what you wrote there, okay? Because as I think you're going
Okay.
to get confused. I do not want you to start fighting with the English.
Okay.
So
Okay.
read what
Okay.
you
Okay.
have there and do as you are. The program works as it, okay? So don't be
Okay.
confused.
Okay. Um, mm, we must save the register first of all. Okay. And in this case, I save the status processor too, even if is seem to be useless. Um, one more time is not the problem in this case.
Yes.
Okay. First, mate, there are two ways to save registers. All expert knows that, but I I I say that for all people. First method to save register: removing, restoring. Sorry. If we want to save a, x, and y, we can use stack again using PHA, that is push accumulator, and PLA, pull accumulator. That is the only way to save and retrieve something from the accumulator instead of PHP and PLP. Okay. So if we want to save A, X, and Y on stack, first of all, we must save accumulator. Then we must transfer X and Y to accumulator, and finally put it to the stack. These are the code. First of all, I save the uh, um, the value of accumulator into the stack. So I take the X value and transfer it to the accumulator, and I save again the accumulator that have a value of X in this case. So in the last part, I transfer Y value to the accumulator and push the accumulator to the stack. In this way, I saved on the accumulator the on the stack, sorry, the accumulator, the X value, and the Y value. Okay.
Okay, Emmanuel,
Now,
I stop you there, okay? So you can
okay.
continue. So, first of all, I'd like to thank Proton, okay? He always gives good advice. So, yes, what he said, what Proton said is that we should also set. Yeah, yes, Proton, but I'm afraid you, Emanuele, will get confused. So we're going to proceed with that, but yes, and uh, what I was going to say, yes, Proton is right, and I just want to make you aware that what we are doing here, we are locking it, so nothing else will happen. So we will not have an unmaskable interrupt or uh, that will happen. So we are just trying to show uh, what happens when you disable basic and kernel and you do uh, an interrupt, so that in episode number 4 or in the code of number 4 you will see the raster stabilization. If you have other things going on like what Proton is mentioning, then yes, you need to take care of what Proton is saying. But in our case, we want, the theory is to have how to have a stable raster interrupt. But so please keep that in mind. Yes, Proton. Okay, but you know it's we are trying to explain things. If we go through the depth, we will never finish. But yes. So the important thing is that we explain how to get a stable interrupt, not a stable raster, not the other things that we haven't covered or we need to cover. But please note, Proton is right, and if you have other things going on, you need to take care of these things. It's just right now, bear with the theory, please. I'm just going to say what Emanuele said. He's saving the processor status on the stack, and then he's saving the registers, okay? To save the registers, you need to transfer them to the accumulator to be able to save them. So first he saved the status, then the accumulator, then the X register, okay, with these two, and then the Y register. That's what Emanuele did. I'm following you. Okay, Emanuele, you can continue from here.
Okay, but I want to go to the end to explain
Yeah. Don't explain this part. Just skip.
To explain the contrary. When okay, now the CPU run this part of code and go to the end. At the end, we must restore the values of registers. But when we restore the values, we must restoring the values in the reverse order. Here we have processor status, A accumulator, X accumulator, and Y accumulator. When we are restoring it, we must reverse the order. So take the last value from the stack with the PLA, pull from stack into A register, and transfer it to the Y, because this is the Y value that Y had before the interrupt. So we make the same with the X register, and the last one we restore the accumulator with a simple PLA. So before the RTI, we must retrieve the value of the processor status. In this way, we have saved values before our routine, and here we have retrieved the values in the right order, or better, in the reverse order.
So notice that to restore the registers back, you have to do them in the reverse order. So if you started, Emanuele, I'm taking control again.
Okay.
If you started with saving the processor status on the stack, and then the accumulator, and then the X, and then the Y, when you restore, first you restore the Y, then you restore the X, then you restore the accumulator, and then you restore. Whisper me, Proton, and I will cover it either later on or in the next episode, because yes. So notice that down below they are the opposite. Okay, so notice first is the Y, then the X, then the accumulator, and then the status register, because of the way this deck works. The rest, I believe it's still the same, but yeah. Okay, Emanuele, continue.
Okay.
I'm going to give you control. Yeah.
Okay. The other, there is a second method
Oh, hello, the
that
gaps.
I prefer instead of using the stack is using the auto modifying code. Despite Phaze101 that do not agree with me.
No,
I have a control.
I do not
To
like
save
self-modifying code. No, I do not
sorry,
like self-modifying code. Yes. No matter what
sorry.
other people say, I don't like it. I mean, sometimes I use it, but I don't like it.
Okay. Was a joke.
Yeah, but it's true.
Naturally.
It's true.
Okay. To save a, x, and y using self-modifying code, we can save clock cycle and space. To use this method, we should start from the end. To explain this method, sorry. At the end of the hour code, we should define some labels, one for the A, for the accumulator, one for the X, and one for the Y value. And these three labels are in the middle of the commands LDA, LDA. These labels are the argument of the opcode LDA, LDX, LDY, LDY. So it's like to write load this label in the accumulator, load this label value in the X, load this value in Y. But if we use this label to store the value that we want at the beginning, we solved our problem to save and restore the value. In fact, in the first part of our routine, we save again the processor status with with the stack, because there is no other way to save it. So we take the value of A, X, and Y. Sorry, I see now that I make some typo. So we write the value of A, X, and Y inside of our code in the right position to restore it when the routine is finished. Can you recap my words?
Yes. Yes.
Because
so he is going to save the registers. We can also use self-modifying code. So basically, he is storing, okay, the A, X, and Y register into these memory locations. Kick assembler, okay, has got, you can specify a label, okay, and normally you send the value, but the value will be overwritten in this case. I didn't take control. Now I take.
sorry.
Yeah, it's all right.
Sorry, James.
And basically, when you when you are storing the value, which we have here, let's say the accumulator had the value of 10, okay? So you are storing 10 at this, where the label is, okay? So when you do LDA, you're loading 10, basically, with the value that it had before, okay? So if it had 10 here, okay, you are loading it again with the value that it had, and it does the same thing. This is, I mean, I do not know other assemblers, I have to admit, but this is particular to kick assembler, okay, to store at a memory location. Normally, okay, in other assemblers, I can maybe guide you what they do. Let's say I had label.
Yes,
Okay,
in CBM
what they do
progress.
is STA label +1, for example.
Yes. True.
So here there would be STA label +1. Okay, so to store in that memory location, but kick assembler makes it more easier.
It is more elegant kick assembler in this case.
Yeah. While we are at it.
Sorry, James.
No.
I must. I must say hi to the Jeps because he is a little grumpy.
Okay, so while we are at it, give me a second, guys. I want to show something. So.
Okay. I can continue.
No. Wait. I need to show something.
Okay,
because,
sorry.
So, Proton, okay, was kind enough to share this link about what he was saying about the not to have to save the status register, okay, because it's automatically done. And unfortunately, can I make it bigger? This yeah, the RTI restores the status register, okay? So Emanuele is saving it and the CPU is saving it, and then Emanuele is restoring it, and so basically the PHP can be removed, okay? However, yeah, it is not going to affect the code. It's just that we are saving more info than what we should. But know that it is saving the flags. We can, if you want, we can try it, Emanuele.
Yes. Sir.
If you want, I can try it.
Okay.
Without. This is the code of Emanuele, okay? So I need his permission to modify it.
Can't you modify it?
But I need to disable this.
No.
What?
Ok. Can I? Vabbè. Ok. Continua pure.
No. I will remove it. Don't worry. It's a key for me. I know what you're going to say, but I'm superseding you right now. Because this thing works because of what I told you. It's not really working. Anyway, so just to show you. Yeah, exactly, Proton. It is doing it twice. Yes. So I'm just going to show that those are not needed. And there you go. So those are really not needed. Okay, so the CPU stores the status register before and restores it when you do an RTI. Okay, Emanuele, is that clear also for to you?
Yes.
Okay.
It's clear. It's clear.
Okay. Okay, so let me put the code as it was because I know you will panic.
Okay. No panic. It was a pity.
Okay, I'm going to give you control.
Okay. This part of the code is is identically to the other. Anyway, after saving saved the registers, we change the border color. We are in the border color in this moment. We wait some cycle and we change again the border color to return back. In fact, we using the ink opcode to add one to the actual color and deck the register DO20 that is the register for the border color control. In this way, we will display a little horizontal line. Here we acknowledge the ERQ register DO19 to
Emanuele, I
avoid
have to ask
that.
you, Emanuele, I
Sorry.
have to ask you to start again from here, where we changed the border because I was not following you and the screen was still at the bottom. So where we changed the borders, okay?
Well, here we change the border, incrementing the border register. So we wait some cycles to make the line bigger. So we decrementing again the border register to have to coming back to the original color. In this way, we will display a little line, horizontal line on the border at the 30 raster line. After that, we have to acknowledge the ERQ register, clearing the ERQ bit because if we're not clearing it, the ERQ is triggered every frame. No, is triggered more time every frame. we to clear the I'm repeating the
Yeah.
explanation of the last the, the last time.
Yeah, so this part we explained it last time. Basically, we are changing the border. I will explain it, Emanuele, so that you can
Yes,
take
yes,
a
yes.
rest.
Thank you.
But we're changing the border, okay? Incrementing the border color. We wait a certain amount of cycles, okay? And then we decrement again. So if it was blue and it became white, let's say, or gray, whatever, then we decrement again and it will become blue again. Using the ASL instruction, okay? ASL does, we explained this last time, does a read, sorry, it does a write. And the first time it does a write is it writes all once and then it sets the value. Because of the way this instruction works, it basically indicates to the VIC that the interrupt has been served. Okay, we have
Yes.
acknowledged the interrupt. Okay, so that's what he's doing with why we have this ASL instruction. If you notice, okay, the code is very simple. We are just storing the registers, okay? In this case, we're using the second method. We're just changing the border, okay, color for a little bit. Then we acknowledge the interrupt and restore the registers and return back to the OS. And because of that, well, not return back to the OS, but you know what I mean by our infinite loop.
Yes.
By
Our
doing
routine
that,
is sorry.
you see here, you see that we still do not have a stable raster interrupt, stable raster, but we are incrementing the color from blue, it comes gray, I believe. Then when we decrement again, it comes to blue, and it's happening on raster line 30. Okay. In the next code, we will show how to stabilize that, basically.
Yes. Comparing this this program, this output with the output of the other episode, we can see that the line is placed in a different position. It start from a different position from the other episode to this. In this episode is placed before in the first half of the raster line. In the other episode was in the second half of the raster line, because the interrupt, the real interrupt is triggered with less cycles, compared to the cycles used to call the interrupt when the OS, the basic and the kernel are switched on.
Okay, so Emanuele, I think we can start the number 4, no?
Yes. Okay. This is
Okay, so before Emanuele actually starts talking, I don't think we have time to finish this one today, okay? But we will start talking about it and then uh, we will continue next week. It's a bit more long than the previous one, and yeah, it's what it is.
Okay. In this example, I made the raster stabilization. The line that we seen before will be fixed,
Will be
will be in a
stabilized.
fixed position of
Yeah,
the screen.
will be in a stabilized position. Emanuele, read your notes. I remind you that.
Yes. Okay. In this case, most of the time, to tell true, the CPU complete the operation it was doing before serving the interrupt call. No, sorry, I'm starting reading okay. The flicker of the line in the other episodes is due to the fact that the interrupt that displayed the line may be requested at any time, even when the CPU is in the middle of completing an operation. In this case, most of the time, to tell the truth, the CPU completes the operation it was doing before serving the interrupt call. This unknown delay, also known as jitter, causes uncertainty about the exact moment in which the interrupt is handled, hence it results in a flicker in our example. Consider the next 4 lines of code. CLC is an opcode that clear the carry, is a flag of the register, of the status register. We load a value in accumulator, so we add a value to the accumulator and we place the value of the accumulator in a memory. Okay, is not important where. Okay, the important is the examples. In the first examples, we have an interrupt in the middle of the first two opcodes. When this happens, the delay that I said before is of 0 cycle. But if an interrupt occurs during an opcode which hasn't finished like the interrupt 2, okay, here in this opcode that that uses 5 cycles, assuming that interrupt occurs after first cycle of this opcode and before the last cycle, the fifth one, the interrupt can be served with a delay that will have a range from 1 to 4 cycles. So our uncertainty or jitter is of 4 cycles. The stabilization of the interrupt allows you to completely clear the jitter or uncertainty. Therefore, you need to know how many clock cycles the raster is from the far left. Clearing this uncertainty allows us to start drawing our line at a specific point in the raster line without flickering. It must be said that the stabilization of the raster is not always necessary. There are many things that are no need raster stabilization. but often, in fact, often is sufficient to have an approximate stabilization. I think about if we want to open the upper and lower border, for example. However, if you want to take advantage of some VIC-GFX, graphics effects, like VSP, that is a technique to move the entire screen in the eyebrows blink. Then knowing
In the
stabilization,
blink of an eye.
the blink of an eye, thank you. The knowing stabilization or synchronization is an absolutely must. Okay, here we have our function to of kick assembler to that say where the our code starts. We have some constant like our raster goal is the raster line where we make stabilization, that is line 30 this time like the other time, but this time we should use another raster, another constant. This constant is called raster myRQ. That is equal to raster goal, the line minus 2 y. Raster line where we make stabilization in order to stabilize the IRQ at raster line 30, we need to start the stabilization procedure 2 cycles before that. That is raster line 28.
Yeah.
The actual raster line is used at the beginning of all. Our real starting point for our service routine, interrupt service routine is line 28 to reach line 30 stabilized. Okay, here we have our VIC register constant like raster DO12, DO11, DO19, and the control register DO1A. This time I used a constant to memorize it. Okay.
Emanuele, let me say what you said.
Okay.
So, I'm not going to read it all, okay? But I'm just going to cover the basics, the most crucial, I think. So, first of all, you can have an interrupt that happens. You can have an interrupt that happens between one opcode and another. Okay? In that case, we have a 0 delay. But if an interrupt happens while this instruction is being executed, which is 5 cycles, then this is what causes the time difference, because there is a delay before
a delay before the
gets
setting
executed. Okay. The crucial point that Emanuele said is that to get a stable raster line, you need to start 2 raster lines before. So if we want to have a stable raster on raster line 30, we start on raster line 28. So the goal minus 2. Okay, that's the crucial parts of this.
Yes.
Okay, so Emanuele, can you please continue?
Okay. In this program where we stabilize the raster line, I used a technique called the double interrupt. Okay, stabilization with double interrupt. Why double interrupt? Because effectively,
Mm-hmm.
we use two interrupts instead of one, or instead of only one. We will see what is the second interrupt. Okay, and this is this is why the cause, because why we use this different raster to initiate all. Okay, like before, we disable interrupts. We disable the C. We must disable the CIA interrupts and the eventually queued interrupts on CIA chips. So we switching off basic and the kernel again. This time I called my routine pre my ERQ to highlight the fact that this is the first of two interrupt. Okay, so I load the low and the high byte like before. I place the low and the high byte in the vector, in the interrupt vector. I load my ERQ value of the interrupt that is two raster line before the line where I want the stabilization, and place it on the raster register DO12, like some minutes ago with the other program. So now I place 0 in the bit 7 of the register DO11, and I activate the interrupt, the raster interrupt using the ERQ VIC register DO1A. And finally, I reactivate interrupts, the interrupts. So here we have our infinite loop like the other program that increment the first byte of the screen at the upper left corner. Here we have my ERQ routine.
Okay, Emanuele, I'm going to stop you a bit because
yes.
I realized that the screen was not scrolling with yours when you were scrolling, but yeah. So
you are not following me?
Yeah. So now I'm just going to explain it. Just anyway, it's similar to what we had before, so it's not a big thing. So again, we disable the interrupts. We clear also. So here we are disabling them, and we are clearing the interrupts. Here we are setting the same configuration that we had in the previous example, where we are disabling the kernel and the basic. We are pointing to our IRQ, okay, and storing it. Once we've done that, we are setting where the raster interrupt will happen, okay, which it is on line 30, right, if I remember correctly. Then we indicate that we want a raster interrupt, okay, and once we've done that, we enter the same loop that we had in the previous example. I am going to show this example because we should always show the example before we start. As you can see, this code has a stable raster line. And the first part was exactly the same as the previous example, but now we will, Emanuela will be showing how this was achieved, okay? I give you control. Okay.
Okay. Are you following me?
I am following you now, yes.
Okay. This is the start of my interrupt routine. Okay. This time, despite the last time, is important to count what? To count every single cycle. Because the stabilization, we can do a stabilization if we if we position the our program counter exactly at the same place of the raster line, the raster beam. So the annotation used, such as R50C2025, indicates raster line 50, 50 and cycles between 20 and 25. Is a mode to is a kind to see the guitar in that lines, in that line. The number in square brackets next to the opcode indicate the cycle used by the opcode themselves. The number after the arrow, the right indicating arrow, indicate the range of finished cycles. So, saving the status of this, I save the status of the CPU register with the stack. Okay. But before I must say a thing. When the ERQ call my routine, it uses from 7 to 14 cycles. So my routine will start at the line 28 in this case, but I don't know where I'm starting. I know only that I can be it can be from 7 to 14 cycle. It's clear. Okay. So I'm here. I'm in the row 28 between cycle 7 and 14. First things, like previous one program, I save the registers. Here we count how many cycle is used, are used, and at the end of this part, we are in the row 28, but cycles are from 20 to 27. We have a guitar of 7 cycles again. Nothing is changed. Summary. Okay. A normal raster line use 63 cycle in PAL mode to go from the left to the right edge. When the interrupt is triggered, 7 cycles are used by the interrupt. 0 from 7 cycles are used to complete the last opcode operation interrupted by the interrupt. Okay. The example was at the beginning. In this example we have a guitar of 4 cycles, but the opcodes of Commodore 6502 can be can use from 2 cycle to 8 cycle. So the maximum number of cycle of guitar the maximum number of cycle used to complete an operation are 7. So coming back, the hour, so we have 0 from 7 cycle used to complete the operation before the interrupt can call my routine. 13 cycles are used to save the various register and status processor in the stack. These are the 13 cycles that I used. Okay. So now we are in row 28 cycle from 20 to 27 with a degree of impression jitter of 7 cycles. Stabilization allows us to have a degree of precision equal to 0. More info. Okay, now we are inside. Okay, now we must reduce the jitter. To reduce the jitter, the tricky part of this code is to to activate again the interrupts and assuring us to trigger the interrupt in an opcode of 2 cycle. We say this in a minute. So if we are sure that the interrupt is called with inside an operation of 2 cycle, our gitter become from 7 to 1. Okay, we have at the end we will have an imprecision of 1 cycle.
Emanuele,
Say me. Tell me.
Okay, nothing. I thought it was not moving the screen, but it's okay. Continue, sorry.
Okay.
I was just checking.
Okay. We are now inside an interrupt routine. Hence, the interrupts are disabled. When we are inside a interrupt service routine, the interrupts are disabled. So no other interrupts can interrupt my routine.
Emanuele, sorry. Highlight the text where you are right now. It doesn't look like it's following you, or I don't know. Where are you right now? Line number.
2035.
235, you mean?
235. Sorry.
Yeah. Start highlighting the text because I don't think it's always following you this.
Okay. Sorry. I'm here. Okay. The trick is to control them and to control the interrupts and make sure that the interrupt fires in the next raster line. We will simply the next raster line. We are in the 28th position. We want to make an interrupt that will trigger in the 29th position. We will simply wait for the interrupt and make it happen at the point when there is an op command. This is the tricky. The interrupt that we will enable will be triggered in an op command, no operation command. The op command uses 2 cycle. So our gitter can be 0 cycle or 1 cycle. We have reduced it from 7 to 1. Okay. In this way, the gitter will be only 1 cycle. Okay. I repeat, we are on the raster line 28. Now we take two the low byte and the high byte of our routine used to stabilize the raster. Okay, and place the low byte and the high byte in the vector, in the interrupt vector. So I increment the raster register that is DO12. Okay, I remember you that now the raster have a value of 28. Okay, using int after this opcode, the raster will be 29. I acknowledge ERQ Now I make the tricky for this technique. When an interrupt occurs, the interrupt save register, save processor status, save other things that in the stack. So if we now will enable the interrupt, we have to assure that all that things are properly managed. Okay. To make this, we save the stack pointer to the X register. The stack pointer is is a value that indicate us where is the stack in how full is the stack in that moment.
No, it
Okay.
indicates where the position of the stack pointer, where the stack is.
Yes, where the stack is. So we save this pointer and we activate the interrupts. So from now, sorry, from this point, we know that the next raster interrupt will trigger on line 29 because we have re-enabled the interrupts. In this at this point, I write some NOP commands. How do you see? Why? I write some NOP commands to reach the cycle 63. That is the last cycle of the line of a raster of every raster line. In this way, I know that my next raster beam interrupt will occurs in one of these opcodes that are all NOP. Okay. When for example, if our interrupt will occur here, okay, our program take this farà partire il trigger esattamente 1 o 0 o con una imprecisione di 0 o un jitter.
Ok.
Puoi aiutarmi, scusa James, mi sono incartato.
Okay, say it again slowly in Italian though, because you said it fast in a way.
Non ho capito, scusa.
Say it in Italian, but slower, because you said it fast.
Ah, ok. No, volevo dire che ho messo tanti NOP per poter arrivare alla fine della raster line.
Okay.
In modo tale da essere sicuro
wait, one sentence at a time, because else I will not be able to translate everything. So, he added a lot of no-op so that he can arrive till the end of the raster line. Remember, each raster line takes 63 cycles. That's why he added those no-ops. Continue. But one sentence at a time, Emanuele, else I will not be able. I'm not a translator per se.
Ok. In questo modo mi assicuro che l'interrupt cada in un opcode di questi con l'asterisco.
So like this, okay? the interrupt will happen in one of these no-op cycles. So an no-op is just 2 cycles, okay? So in the end, we only can have a difference of 1 or 0, basically. Continue. I mean, I don't know if I was ahead now, but yeah.
Okay.
Continue, Emanuele.
And, I can continue reading my notes.
Yeah.
Okay. The ERQ will take place between one of the nodes with the asterisk. We have certainly exceeded the 63 cycles with an opcode of 2 when the raster ERQ is snapped. So I arrived here at line 29 with this uncertainty. At this point, the ERQ activated above has been done, but now 7 cycles were used by the interrupt like before to save various various things like register status and other things. But now we have only 0 or 1 cycle used to complete the last operation that I remember to you that was an op. So we have only 1 cycle of jitter. This is the hour grade degree of uncertainty. We are therefore positioned after row 29 and on cycle 7 or 8. Our goal now is to eliminate this jitter of 1 cycle. Okay, so we reset now. We reset the stack pointer to the value we had before this interrupt. That is the second interrupt. This is because it's called two interrupt method. Okay. So as to make the CPU believe it never happened. After that second interrupt, the CPU have no clue to say what happened in the middle of our routine with this, because we restore the stack pointer. We are on the raster line 29 at the 9th or 10th cycle now, because TXS have used the other 2 cycles. Okay. Now, this is another tricky, a very good tricky.
Can I stop you a second?
Yes.
So I don't think we're going to have time to explain the code, all of this, of what we have. So either we finish where till you reach line 30 till here, okay?
We should finish now, because
so no, I'm just telling you, okay? We both needs to work, so we cannot stay here forever. So either you finish when you are on raster line 130, sorry, 30, not 130, okay? Or you finish before you start explaining the my IRQ. Okay, so
here at 326.
So 328. Either you stop at line 328,
Okay.
or you stop at line 326. Yeah, 326. Yeah, it's the same thing. What I was saying, I didn't
The same
realize.
thing.
Yeah. Um, Another thing I want to add, okay? This technique of having a raster line stabilized, okay? It's not, written in stone. I'm pretty sure there are other people which will be able to do it maybe in a better way than the way we are showing it. However, with all this, I haven't seen anyone streaming it yet. Okay? So we are giving you, okay, what we know and what we know. Okay, Emanuele, you can continue the last bit.
Okay. Where we are? Okay. This is the tricky part. Another tricky part, a beautiful tricky part for me. Is a beautiful. Now our goal is to reach the 30 line of raster. So we starting with a cycle to lose 41 cycles with this loop. This loop is a simple loop that do nothing. The it's only consume 41 cycles. Is a simple one. Load y with the number 8. So decrement y. So using 2 cycle at the beginning, 2 cycle every decrementing, and loop again on the decrementing the decrement of y if y while until y is different from 0. This the depending on the depending on the result of this comparing,
Yeah.
the number of cycles used are different, because if this opcode is take if y is different from 0, it takes 2 cycles. If y is 0, it takes 3 cycles. When y is 0, the cycles the program counter exit from the cycle. So in this at this point we have lost 41 cycles, and we are in the row 29 on the cycle 50 or 51. Here I use the free no operation again to lose other 6 cycles. And now the routine, the best routine, the very tricky routine of this part. To get the 64 cycles and then reach the row 30 and on the third cycle, of this raster, we have to use another 8 or 9 cycles. We are in the 57, 56, 57. To reach 64, we must have other 8 or 9 cycles, depending on jitter, 8 or 9. The degree of precision we will have to be between 0 or 1. In the next line, we will be able to reduce the jitter to 0, and we will be synchronized in row 30, cycle 03. Anyway, the routine starts from here. I load the raster value. So in this at this point, I load where the raster is. The raster now is 29, and place the raster value to the accumulator. So I compare the raster with the raster line. Okay. With the I compare it again. So if we are reading the current, if the last operation ends at loop 64, okay, on the next line the jitter is 1. The next jump for equal will only take 2 cycle clock, as the raster line has changed between LDA and CMP. In this case, the raster line can be changed between year and year. Okay. If instead the CMP ends in okay. If instead the CMP ends in row 29, cycle 73, then the raster line has no changed, and VIC2 will be 3 cycles. In any case, the VIC2, that is the comparing the comparing opcode, my program counter will reach this point. It reached this point with 2 cycle, using 2 cycle or 3 cycle, depending on the jitter. So in this way, I zeroing the jitter, and here my raster line is stabilized with the program counter. And now I can act in the right manner to show my raster line stabilized.
Okay, so the last part of this will be done next week, but we will also do a revision of it because I can understand that there is too much to take. Okay, I think just give me a second. I think
It's quite difficult, this part.
Well, difficult. It's the counting of the cycles and knowing what you are doing. I just saw something and I'm just going to check. Maybe you read it wrongly. Yeah, this part, I think if it's not equal to 0, you're saying it's 2 cycles, and if it is equal to 0, it is 3 cycles. I think it's the opposite way around, as also indicated by Proton. Yeah, I think this should be 3, and this should be 2. Okay, so I'm going to repeat what Emanuele said, okay? So, on line 28, okay, we have taken this amount of cycles for storing the registers, okay? We have taken these, on line 28, we have taken this amount of cycles, okay, and then we filled up with no op, because each line is 63 cycles, okay? After that, we are on line, we save the stack pointer, okay, and we are on raster line 29, okay? The same thing, we have, let's say, a branch depending on the value, whether it's at 0 or not. As I said, these can be swapped or not. The theory is still the same, and one doesn't need to make...
We use 41
Sorry?
cycles.
Sorry?
We use anyway 41 cycles.
Yes,
I check
exactly.
again,
it's always the same cycles. It's going to use the same cycles, exactly. And we add more no ops so that we arrive at 64 cycles with a difference of 1 or 0. Then we load our raster, right? And compare why sorry, I have to ask the question because I'm lost.
Yes.
Why
Right.
why are we loading the raster and comparing to it and then branching?
We are okay. We load the raster here. Okay. We load the actual raster line, and we compare it with
Ciao Andrea, ciao Pippo.
in the second in the next opcode. So if cycle 23 occurs between here and here, this VIC2 change and this taking or not taking change the 2 or 3 cycle used to make the branch. Okay. Anyway, I use my branch to branch to jump in the next in the next opcode. So in this way, I zeroing the guitar.
Okay.
Here I used sorry. Here I used the first 8 cycles. This is used to use the 9th cycles or not. Cioè, sorry, the other 2 cycle or 3 cycle. Anyway, I'm here at the row 13 cycle, 3rd cycle.
Guys, thank you very much. As I said, we will repeat this next week. Hope we'll continue next next Tuesday. And yeah, Emanuele, from your side, you want to
Hi
say?
all.
Yeah,
Thank you for hearing me.
yeah. So guys, thank you very much, and I appreciate that this was not an easy one. Okay, thank you. Bye bye.
Bye all.